we're going to do page 15 and 16. This is a little bit different than normal because since section F was so short and section G was so long, I put the beginning of section G at the end of page 16. Section F. So to solve this equation for x, we take the log base 10 of both sides. And you guys have been doing this for a few pages now. So if I want to figure out what x is, I take log of 10 to the x, and then I put log of 30. And if I do that, then I'm going to get x equals log of 30. Okay, and do you see how the log and the 10 cancel each other out because they're inverse functions? So that's why we're left with just x. Okay, what about e to the x? If we have e to the x equals 30, how do we find x now? Well, we conveniently have natural log, right? Natural log of e to the x is equal to natural log of 30, and natural log and e cancel each other out. So then you're left with x equals natural log of 30. And on the calculator, you have a natural log button and a log base 10 button to calculate those. Now, what if you have a strange exponent like 2? What do you do now? Well, believe it or not, you can still take any log of both sides and it'll still lead you to the answer. Watch how this happens. So let's take the log base 10 of both sides. Okay, now why does this lead you closer to the answer of what x equals to? Well, remember this rule. So if you have a to the n, you can put n out front. Okay, so let's see. Since we have 2 to the x, what we can do is say x log of 2 is equal to the log of 30. And log of 30 and log of 2 are just numbers. So we can divide both sides by log 2 and we'll get x equals log of 30 divided by log of 2. Okay? And so now we already have an answer that's already a number. If we put the log 30 and log 2 in the calculator, we can figure out exactly what x is. So we were able to solve it using log base 10, even though the exponent is not base 10. Now, where did this 2 come from? Well, you can see that the 2 came from the base of the exponent. So basically, if you have this situation, you're going to end up with log, the base of the exponent that you're using in the denominator. Okay? So now we have the change of base rule. The change of base rule is basically, hey, if you have a weird base like 2 to the x and you want to find out what x is, let's say you have 50 here, then what you're going to do is you're going to say x is equal to the log of 50 divided by the log of 2. And it doesn't have to be log base 10. You could do natural log too. You could do natural log of 50 divided by natural log of 2, and it would also give you the same answer. Okay, so that's the change of base rule. Let's go down and work a few examples. So here's the change of base rule right here. They wrote it formally with variables. And so they're saying find just 3 significant figures, some of these logs. So for example, log base 3 of 12. So we already know that that would be log of 12. Base 10, of course, because we can't find log base 3 on our calculator. And log base 3, or log base 10 of 3. And then like we want to find C too. C would be log of 0.067 divided by log of 3, because 3 is the base. Okay, so let's use the calculator and figure out what those would be. Okay, so we're going to take log base 12 divided by log base 3 and it gives us 2.26. Okay, and then what about the other one? Log 0.067 divided by the log of 3. We get negative 2.46. Okay? Alright, let's move on. Use the rule log base b of a is equal to natural log of a over natural log of b to solve correct 3 significant figures. Let's see, so we're going to do a and c. So for a, we have 2 to the x equals 0.051. What we're going to do is we're going to take the natural log of both sides. Natural log of 0.051. And then we're going to put the x out front, right? You can go right to this rule, and you don't need to go through all this, but sometimes it helps to understand where it came from. Okay? And so if you were on the calculus on your calculator, you would go natural log ln 0.051 divided by ln 2. You get negative 4.29. Now, now let's do C. This is kind of a strange one. It's got 2x plus 1 in the exponent. But you don't do anything different, just a little bit more algebra at the end. So let's take natural log of both sides. So get natural log of 3 to the 2x plus 1 equals natural log of 4.069. And then that means that we can take the exponent and multiply it out front. Log of 3 is equal to log of 4.069. And then we can divide both sides by natural log of 3, which helps us to isolate the x. Now we have 2x plus 1 equals log of 4.069 divided by natural log of 3. Now we can subtract 1 from both sides. Get rid of the 1. Now we can divide both sides by 2. And now we have x equals natural log 4.069 divided by natural log of 3 minus 1, all divided by 2. Which, if we put natural log 4.069, natural log of 3 in the calculator, we can find a number for that. Okay? So you're supposed to find that to 3 significant figures. Now let's do number 3a. So you can see that this is a like one of those quadratics where you need to do a gin-cell substitution. From the looks of it, it looks like this is 5x squared minus 3 times 5 to the x equals 0. So let's say that t equals 5 to the x, and then we have t squared minus 3t equals 0, which is t times t minus 3 equals 0. So the solutions are t equals 0 or t equals 3. So 5 to the x is equal to 0, or 5 to the x is equal to 3. We know that 5 to the x can never be 0 because there's a horizontal asymptote at 0. And so for 5 to the x equals 3, we could take the natural log of both sides. We would have x natural log 5 is equal to natural log of 3. And then we will divide both sides by natural log of 5. And then we'll have x equals natural log of 3 divided by natural log of 5. Okay? And then we're going to do C. This is basically 2 to the x minus 2 times 2 to the x squared equals 0. So we'll say that t equals 2 to the x, which means we have 2 minus 2t squared equals 0. factor out a t. We have t times quantity, 1 minus 2t equals 0. So the two solutions are t equals 0 or t equals negative or positive 1/2. So 2 to the x is equal to 0, or 2 to the x is equal to 1/2. We know that 2 to the x can never equal 0 because of the horizontal asymptote at 0. So, and here we can just see that the x here could be -1 because 2 to the -1 is equal to 1/2. So that's the solution. Now last one. Solve for x exactly. Log base 4 of x cubed plus log base 2 of square root of x is equal to 8. So first we can take instead of log base 4 of x cubed, what we'll do is we'll do log of x cubed divided by log of 4. And then here, instead of log base 2 of square root of x, we'll do log of x to the 1/2 divided by log of 2. And then that's equal to 8. And then since we have the log of x cubed, the log of x to the 1/2, we can put the exponent out front. So that would be 3 log of x over log of 4 plus 1/2 log of x divided by log of 2 is equal to 8. Now we're going to multiply both sides by log 4 times log 2, log 4 times log 2, and that'll give us log 2 times 3 times log x plus log 4 times 1/2 times log x is equal to 8 times log 4 log 2. Now we can factor out the log x, and then we'll get log 2, we'll get 3 log 2 plus 1/2 log 4 equals 8 times log 4 times log 2. Okay, and now to find x, we just have to divide both sides by 3 log 2 plus 1/2 log 4. Okay. And then to figure out exactly what x is, log of x is equal to this expression. So 10 to both sides would be equal to, then you'd have x equals 10 to the, and then you'd have this big expression here, 8 log of 2 times log of 4, and underneath you have 3 log of 2 plus 1/2 log of 4. Okay? Okay. So that was section F, and now we're going to just introduce section G. What is the equation of the horizontal asymptote for the exponential function a to the x? Well, the exponential function, remember, looks kind of like this, and it always kind of approaches 0 unless there's a factor on it. So we'll say that the horizontal asymptote is y equals 0. What values of a makes the function increase? Well, if a is greater than 1, the function increases. Okay? And if a is less than 1, then the function decreases. Okay? And but a is greater than 0. What is the value of the function f of x when x equals 0? Well, a to the 0, a to the x equals 0, you know is always 1. Using the variable interchange method, find the inverse function of f of x. So f of x is equal to a to the x, and variable interchange, you say x equals a to the y, and then you solve for y. Now, to solve for y, you need to take the log of both sides, which would be y log of a. So y is equal to log of x divided by log of a. Log of a. Okay? Or, you know, if you're doing log base a, it could just be log base a of x. Okay, if you happen to have, if it's like 10 to the x, or if it's natural log, then you could do that. Okay, so this is what we have here. So the domain of a to the x, we could say it's any real number. The range of a to the x we know is only positive numbers. So when you have an inverse function, you know you reverse these. So this would be x is, it's only works for x greater than 1, and the range is any real number. We know that the asymptote equation for the exponential is that, and so the inverse we would just have x equals 0. We can only find the log of positive numbers, right? Okay. And now we just have 3 quick graphs we're going to do here. Find the following functions f. Find the domain and range, find any asymptotes, axes, intercepts, and solve when f of x equals -1. Algebraically, check solution on your graph, find inverse function -1, explain how to verify your answer. So the first one is log base 3 of x plus 1. Okay, so it helps to make a chart. So let's do a few easy numbers. It only works for x is greater than -1, so we'll do -1, 0, 1, 2. Okay, so if you put -1 in there, it would be log base 3 of 0. Log of 0 is just, you know, an asymptote. Okay, so it would be like negative infinity. You don't have to know that though. Then log base 0 plus 1 would be log of 1. Log base 3 of 1 is 0. Log base 1 plus 1 would be log base 3 of 2. It's kind of hard to say what that is without using the calculator. Log x equals 2, that would be log base 3 of 3. Log base 3 of 3 would be 1. Okay, so if we're going to graph some of these points now, we would have, remember the log function looks kind of like this, okay? So we're looking for something like that. So x equals -1, and that would be log base 3 of 0. There's no defined value for that. So actually there's no defined value for left of that, okay? And then we're going to put point 2 would give us y equals 1. Okay. And then 0 gives us 0. So now we kind of can graph it already. Okay, like that. And then we already found the asymptote. The asymptote is x equals -1, right? That's the asymptote. And the axes intercept are basically 0, 0. And sketch the graph, we did. Solve f of x equals -1 algebraically and check your solution on your graph. So let's put f of x equals -1. We'll put log base 3 of x plus 1 equals -1. And then we will take, you know, 3 to each side, 3 to the log 3 x plus 1 and 3 to the negative 1. That'll give us, these will cancel each other out, so we get x plus 1 equals 1/3. Then we get x equals, and we subtract 1 from both sides, x equals to negative 2/3. So at x equals negative 2/3, y equals negative 1. So we get one more point there. Find f of negative f inverse x and explain how to verify your answer. The easiest way to do it is to reflect the graph on the y equals, reflect the graph on the y equals x-axis, which would be like that, okay? So that would mean we would have something like 2, something like that, right? Okay. Now we're going to do C, which is log base 5 of quantity x minus 2, minus 2. And so some of the convenient points we're going to use are x equals 2, x equals 3, and x equals 7. We're going to see why in a second. When we put x equals 2 in there, it's going to give us 2 minus 2, which is 0. Log of 0 is, undefined. So we know that there's an asymptote at x equals 2. At x equals 3, we get 3 minus 2, which is 1. Log base 5 of 1 is going to be 0. Minus 2 is negative 2. Log base 5 of 7 minus 2 would be log base 5 of 5. That would be 1. Minus 2 would be negative 1. So with these 3 points, we can graph most of it. So let's put the asymptote at x equals 2. And then we'll put the, mark the point 3 comma negative 2. That would be here. And then we'll mark the point 7 comma negative 1. And I think I made the axes too far to the right. So here is one of the advantages of doing it on the iPad. Okay, so 3 comma negative 2, and then is that far enough over? 4, 5, 6, 7 comma negative 1 would be there. So that would be, oops, I got to move the points too. Okay, there we go. 3 comma negative 1. So it looks kind of like that. Okay, all right. And the asymptote is x equals 2, and the axes intercept, that's it's kind of hard to figure out. And f of x equals negative 1, we already figured that out, it's here. Find f of negative 1, and remember, you want to take the reflection about the y equals x line. So you would have something, up here somewhere, okay? And then the last one, I won't do all the way, but again, you make a chart with x's and y's, and you can see that there's going to be an asymptote at x equals 0, and then when you put 1 in there, you're going to have a special point. When you put 2 in there, you have a special point. When you put 1 in there, you get log base 2 of 1 is 0, so then your y is going to be 0. When you put 2 in there, your log base 2 of 2 is going to be 1. Multiplied by negative 2, you get negative 2. Plus 1 is negative 1. So you can graph these points 1 comma 1 and 2 negative 1, and you're going to get another log. And in this case, the log graph is going to look upside down because it's subtract the log. Okay? So that's it for today. Sorry it was so